mainly to follow our discussions for the second session 2, that the main block is the thermochemical routes to renewable liquid gas. I'd like to invite Dr. Kamal Kalsi, CEO from Circular Fuels Limited UK, to talk about the Syngas to renewable demethylator. So thank you, Kamal, and the floor is yours.
Okay, thank you very much. Perfect. Well, it's good to be here and to have listened to all the very interesting conversations beforehand. I think they're all very, very pertinent. I think some of the discussions, especially regarding biomasses and what sort of feedstock ends up in what product, hopefully I can shed some technology light to that in the coming discussion. Next slide, please. Okay, so very briefly, so Q Technology, we're a pressurized gasification technology company, and our mission is to convert waste and lower grade feedstocks, so agricultural biomasses and so on and so forth, which are a very important theme in this discussion regarding Brazil, into a high quality syngas vector, so into a gas containing hydrogen and CO, which really then forms the building block for doing many other things with. We have a 10-year history, and that has sort of culminated in the development of a full-scale product demonstrator in Wednesbury. This is near Birmingham in the UK. We've had quite a long history, if you go to the next slide, please, where we were supported quite heavily by the UK government in the beginning in order to construct a full-scale demonstrator, because gasification as a technology route is very interesting, because if you're using a high biogenic content and it opens a route for carbon capture, with even a reasonable degree of carbon capture, one can start producing negative carbon fuels. And this I think makes it extremely attractive, because some things which are impossible to decarbonize completely, well, a negative carbon fuel really does offset that. So we've worked very heavily, obviously in parallel with the development of the technology itself, actually also on understanding the market and also on understanding the general flow of policy and feedstocks, and which is the right product. Are you talking about hydrogen? Are you talking about distillate fuels and making secondary fuels, methanol, ethanol? Are you talking about LPG and LPG substitutes? So we've had the good fortune of working quite heavily across these different feedstock types, across these different end use types, and analyzing them in some detail to really try and converge the technology and converge the product solution into what the market, what is attractive ultimately for the market. Obviously, as part of all of this, we formed some very good relationships, commercial relationships with major players, SHV Energy being our most recent relationship. We have a joint venture with SHV Energy called Circular Fuels Limited. The objective of Circular Fuels Limited is to develop commercial scale bulk DME production plants using waste and low grade biomasses as a starting point. So if we go to the next slide, please. So really, in terms of where we sit as a technology, we're in between two parallels. The first one being decarbonization. So clearly decarbonization and providing lower carbon feedstocks and fuels is a core part of what we do. But we also sit on the other side, which is waste reduction. So waste is something that touches everybody. This has been part of a very core element. I think somebody mentioned in the earlier part of the session about biomass and how we have to be careful with how biomass is used for fuel production, because it could lead to deforestation. And we are very much of the view that the feedstock that we begin with has to be a waste, or has to be an end-of-life product, whether it's agricultural waste or whether it's a municipal waste, a derivative product. It really has to start from that, and therefore you do not go and interfere with the food sector. For example, you do not go and interfere with deforestation, but rather you take something that right now people are throwing away in the bin, so to speak. So really we straddle these two sectors. And if we, next slide, please. And so what we are able to do is take these low grade feedstocks and biomass and convert them into this hydrogen and CO production gas. What is unique about the technology and the way we do it is that our gasification system is a high pressure approach. So it, at a smaller scale, this is a fairly unique proposition. They are larger coal gasification plants, of course, but those are fossil based. And really what that does in terms of the technology is it allows it to not only have some technical advantages, so converting lots of different types of waste into a high quality gas vector that we can then convert into other things, but really it's also around the delivery model. So how do you build what is effectively a fairly complex plant anywhere in the world and make it cost effective? So if we go to the next slide, one of the key strengths of the technology is really about being able to take a very variable feedstock like waste, because one minute you have plastic, then you have biomass, then you have something else that changes, and turn it into a very homogeneous output product. So that technology, the manifestation of it is we have it in our plant in the UK. This is the facility, the pictures that you see in Birmingham, where we have a full-scale demonstrator. So as a result, we can do a lot of work in proving operation all the way to a fuel end product, so an end-to-end demonstration of the entire process, which really acts as a key risk mitigation element in terms of demonstrating the viability of these technologies to solve these problems. So next slide, please. And this is just a graphical representation of that variability I was talking about, where you can have something that is highly variable, it produces a highly variable gas, but our technology's uniqueness lies in being able to convert it into something very, very homogeneous that can then be used for a higher purpose, essentially a synthesis purpose later on. So next slide, please. This was just a very quick demonstration, and this is really the key, especially in the context of the discussions we've been having around this. The technology really lends itself to be able to use everything from sludges, so these are sewage sludges, digestates from anaerobic digestion, refuse-derived fuel, so this is from municipal waste, or indeed from commercial and industrial wastes. We can use woody biomasses as long as of course, the sustainability criteria is correct. So it's more of a commercial problem than technical one. And we can also use other lower grade wastes, which at the moment are it's a struggle to do something with. For example, category 3 aviation waste, hazardous wastes, which today pose health problems. So the advantage really of the solution is that we can take any of these things and we can convert them into a high value end vector. And as we'll see on the next slide, really what is very interesting for us, and our primary focus is on waste. Now, Brazil generates about 80 million tons of municipal solid waste annually, and actually about 40% of that, this is quite staggering, is in controlled landfill open dump, and about 58% of that is in sanitary landfill. So there is a lot of landfill, I think is the short answer in a nutshell in Brazil, and there is therefore a very strong need to do something better. What we're doing right now is taking kilojoules of energy and we're just putting them into the ground, which are then releasing methane, which is then obviously very powerful greenhouse gas and causing further damage. So there's a lot of wasted energy here, and what we're suggesting here is, look, we can tap into this. We can take this and turn it into a fuel vector that cuts across. And even though refuse-derived fuel has a organic proportion, in Brazil it'll be about 60 to 70%, the reality is, yes, there's a small fossil component to it. But in reality, a lot of it is a renewable feedstock, is a renewable origin, and therefore the fuel that you can produce at the end of it has a large renewable component. And you are able to do that actually with a waste stream right now, which already exists, is already there. It's just not being put in the right place. So if we look at the next slide, you can see here actually that there's other opportunities in Brazil as well, right from agricultural residues, crop residues, sugarcane, soya, eucalyptus. And I think the unique thing about the conversion route we're proposing here is that as opposed to anaerobic digestion, or for example, the production of ethanol, where the feedstock specification has to be very tight, you have to rely on a very specific process and a very specific feedstock to produce the end product. In our case, the process is very omnivorous. We're not reliant on cellulosic or non-cellulosic biomasses, for example, for our process. We'll just have anything and everything. And that makes it very effective and very flexible to be able to do in a distributed format. It's a very large country, and the production of these things is split over many, is geographically very dispersed. And as a result, having a technology that can deal with that is quite essential. So next slide, please. And so, and this is just to summarize what I was saying, which is waste is a very excellent feedstock. There's a lot of waste biomass that is available. That is also a very good feedstock. It's sitting there. It's energy that currently right now people are either burning or burying. So there is a better way of dealing with this. And if we look at the next slide, there is, again, this is just a short note on incineration. Obviously, a lot in Europe, especially, incineration is a primary mechanism for disposal of these wastes. But what we're finding right now is that it is increasingly being viewed as just a stopgap solution, and there is a better way. And what we're proposing here is the better way of doing it. And the next slide just demonstrates a little bit why, which at the moment, even the best incineration today takes in and makes electricity. And really, I would say that the approach here is damage limitation. So people are making electricity as a way of limiting the damage. And what we're saying is, why are you making electricity when you can take chemical energy in your feedstock and make chemical energy coming out the other end? Just moving on to the next slide, please. And this is a demonstration just of what I was saying before, which is recycling and reuse is there, and that has to be there. It's a primary way of how we're going to go forward. But instead of now going to recovery as the next, we're saying conversion is an intermediate and better way of using this energy than other approaches. So next slide, please. So this is just a very important point regarding the catchment areas and the relative scale of things. So the typical oil and gas world of producing fuels is to make everything as big as possible. You can possibly make it as big as possible and as expansive as possible. Now, the reality of how waste and biomass is produced is that the catchment areas are generally a lot more limited. So you might have 200,000 to 300,000 tons. This is a European model. You might have a bit more, you might have a bit less in other areas, but generally the scale of your project or the scale of fuel you produce in a single facility is limited by the amount of feedstock you can sensibly collect. There is no point of transporting waste or biomass 1,000 miles in order for a central facility, and really that limits the scale of facility you produce, and therefore that governs what product you want to be producing at that facility. And through a very long analysis that we have done, we find that dimethyl ether, DME, is an extremely good product to produce this way because the process is very simple, it's very effective, it's very efficient, but also it lends itself to being scale efficient. Producing distillates, jet fuel, for example, from this sort of process requires a much larger scale, which makes projects a lot more difficult to do, especially at this early stage. Next slide, please. So DME is extremely important to LPG, of course, and in a very high nutshell, the key thing behind the plants we're proposing is that the DME that's being produced is a direct blend stock for LPG, and it is a bulk supply. So the DME we produce is not a offshoot 3 or 5% of our overall production, but these plants are focused and dedicated on producing DME. This is the backbone behind our joint venture with SHV Energy, which is Circular Fuels Limited. And this particular approach allows really quite an innovative approach in terms of doing it. And initially, of course, you can blend up to 20%, that's the target, and eventually it will go to a much higher blend level. If we go to the next slide, and I'll be closing shortly. So the joint venture we have with SHV Energy, the objective is to produce numerous plants using waste feedstocks to produce the end product, which is DME. We're starting with the first project, which is currently now in development. We've already completed a feed and we're doing a next stage of it, which is in the UK. But really, our remit is global and we'll be looking to develop further projects, especially in places like Brazil, where the feedstock is there, the energy is there. We just need to convert it in the right way. So, yeah, finally, just to close. Yeah, so, and this is just to summarize, there is a very strong desire for circular economy, and we believe that this solution of taking a waste and converting it into a low carbon fuel solution ticks all the boxes and can also be economically viable. Our objective is fossil parity at the very least. We believe we can do better. So that's a closing remark. Thank you.
Thank you very much, Kamal, for your
presentation.
In our session, I invite, in fact, not Professor Harvey, will be replaced by Bogdan, right?
Yes.
Are you here? Okay.
Yes.
So, yeah, I can hear you. So from BTU University, so the floor is yours.
Yes, I would like first to apologize for Harvey because he was scheduled to give his presentation, but he just had his second COVID vaccination and he's not feeling very well. So until he's recovering, yeah, I will take his place for this talk. So now, if you could go next slide, please. So now, the main reason that we are still talking about opportunities of using Syngas for various products is, as you see here, the start or the predictions or the projections in terms of global warming or climate change that need to be tackled somehow. And this, if you go to the next slide, please, are due first. One of the first reasons is the growth of the population that leads further to an increase in energy consumption, and which, as you can see, follow a very close pattern. If you go on the next slide, please. For this reason, many policymakers are asking industry to improve, let's say, their operation in terms of energy demand, which needs to be reduced, the dependency on fossil fuels, the reduction of greenhouse gas emissions, increasing energy efficiency. Now these numbers are from the former climate action plan from the European Commission, which I've seen that yesterday has been updated by the Commission. And for example, for the reduction in the greenhouse gas, I've seen that it has increased from 40 to 55 by 2030. So these numbers may not be accurate anymore. I mean, this is still not decided. It's just a proposal by the Commission, but things may change in the future. So we have quite tight targets for the 2030 currently, which may be even worse in the future. Now, the main routes for achieving these targets towards decarbonization are split into three parts, as you can see in the lower part of the lower figure. So first, the one option would be to reduce the demand for carbon-intensive products and services. The second, to improve the energy efficiency, and the third, to deploy decarbonization technologies across all sectors of the economy. Now, if you go into the next slide, please. Now, since I'm from Germany, of course, Germany also has tight targets towards improving its renewable share, emissions intensity, and energy efficiency. And again, as you see on the figure on the left, they're also getting more tight, or more, the targets are becoming more stringent. If you go on the next slide. So now one solution to achieve these targets would be to implement renewable energy towards low carbon energy systems, low carbon industrial system as well. The issues with this are that in many cases the supply varies, so it's intermittent in many cases, and the best examples are the solar and the wind, which are very easy to understand. And this intermittent supply means that there's always going to be some mismatch between the supply and the demand for this energy, renewable energy. For these reasons, there's an urgent need for solutions to find new ways to store energy when surplus power is unavailable, and also find ways to use the stored energy in sectors that consume a lot of energy. Next slide, please. Now, an approach to ensuring this comes from the power to X type of technologies. And here you have an example which is mostly based on electrolysis. So we have renewable resources on the left. We have use of abundant molecules like CO2, which is captured from various industrial sectors that currently have a high amount of emissions. We have air, we can have, again, emissions of NOx's. We have, again, water, which is abundant in some parts of the world, not everywhere. And then, based on this, we produce, let's say, building blocks like green hydrogen, synthetic hydrocarbons, ammonia, hydrogen peroxide, and then these can be then converted into more advanced chemicals using Haber-Bosch processes, methanation processes, Fischer-Tropsch, and then we obtain all sorts of chemicals. The main benefits of this approaches are, as you can see on the right of the figure, that they enable more decentralized production, so we can produce. We don't need a traditional central type. Things are produced where the main resources are available. We can store the energy in these building blocks and then use it further to enable the decarbonization. If you go on the next slide, please. Now, Syngas, as you all know, is a mixture which typically contains carbon monoxide and hydrogen. And if you go on the next slide, it's a building block for many processes. It's a crucial previous slide, please. It's intermediate resources for various applications in the chemical and not only industry, as you can also see on the figure. Now, on the next slide, the traditional production based on fossil fuels uses solid, liquid, gaseous hydrocarbons, and usually in this case the fossil carbon is oxidized completely. However, if you go on the next slide, more let's say modern or approaches consider carbon dioxide as a starting point for the syngas. And here you have an example also based on electrolysis. and depending on the type of electrolysis, so we can have low temperature, high temperature. We can also use hydrolysis of water to add the extra hydrogen, and we produce our syngas. If you go on the next slide, please. Another set of approaches that will enable the production of syngas come from biomass. You see here that so using thermochemical processes such as gasification, and we had the example from the previous talk, pyrolysis, which I think is one of the next talks. So they're based on the thermical process, we will produce different ratios of CO, so carbon monoxide, carbon dioxide, hydrogen, lower carbon, hydrocarbons, and many other things. But of course, the main feedstock for the further processing would be the syngas, so our hydrogen and carbon monoxide combination. Now, as I mentioned, from gasification, we may also obtain CO2. And again, we can use the reverse water gas shift to convert CO2 to syngas, which may also require some additional hydrogen, because it's possible that the hydrogen that we have from the process may not be sufficient. And in this case, one solution would be to use the electrolysis of water, which will give us the extra hydrogen and also would provide us some oxygen, which can be used in the previous thermochemical process for the processing of the biomass. Now, if you go on the next slide, please. Now, why would we want to use CO2 as a starting point for syngas? Well, first, because we can produce our fuel, our energy, our product while reducing the dependency on fossil fuels. There's plenty of CO2 that needs to be used, either is because it's coming from energy intensive industries like steel, which they need to get rid of. And by using the CO2, we also reduce the the CO2 emissions, the greenhouse gas emissions. If you go on the next slide, please. So in this case, the idea is to use renewably generated electricity, whether it's coming from solar, from wind, to produce syngas using electrolysis as a key enabling step. And again, here we can use the electrolysis of CO2 combined with electrolysis of water, or as I mentioned in the previous slide, biomass, gasification, pyrolysis, thermochemical processing of biomass to convert it into syngas. Now, there are some challenges which will be on the following slide. Some of the challenges that need to be taken into account are the development of new catalytic and reaction systems. Now, I mentioned that for the CO2 or the product gas of the thermochemical processing of the biomass, we need to use the reverse water gas shift to convert the CO2 into CO. So this means that we may need to develop new catalysts to achieve this efficiently. Then we need to use process intensification types of operations to produce new reaction systems or other units that are required in the process, and you see here some examples of microchannel reactors. If you go 2 slides back, please. No. Yes, no, before. Where it's only the new catalytic and reaction system on the slide, please. One extra before. No.
Mr. Ogden?
Yeah.
I just asked you to try to finish, mainly
Okay.
because we are.
Okay. No, I wanted to say, because one other reason why it's important to investigate further is that usually the catalytic system are developed for lab-based or lab recipes of syngas, and industrial ratios may differ. And there is a figure there where we show, based on our research, the impact on the catalyst and the reaction. Then we need, besides this, we need to integrate the new processes into the current technologies or current system, not only with the energy coupling, but also biorefinery type of application, other supply chains for the fuel, supply chains for the biomass. And finally, virtualization. We also need models for the reactors, for the supply chains, for the whole system. And our idea to follow this is a 3D approach, which is the last slide, where we start with the decarbonization by developing new solutions for low carbon technologies. The second will be the decentralization, shifting from centralized to delocalized networks, and here again from biomass supply chains to biofuel supply chains. And there was a discussion in the previous case on how Brazil will handle the fact that they have resources, different resources across the whole place. So decentralization would be one solution. And finally, the digitalization, so development of digital twins, models to handle all these developments. This is all my talk. Thank you for listening, and I will wait for any questions. Thank you.
For your presentation. So we will have questions in the discussion sessions, right? Just to follow our presentations in the session 2, I'd like to invite Professor Dr. José Calors Pinto from University of Federal of Rio de Janeiro to talk about the biodegradation and pyrolysis of plastic residues, perspectives, and LPG productions. So thank you, Professor José, and the floor is yours.
Thank you very much, Priscilla. It's a pleasure to meet you here once again. So it's nice to see you. Thank you. Next slide, please. Yes, I would like to invite you to visit the web pages where we present some general information about our group and the work that we do in the general field of polymerization reactions, which is indeed correlated strongly with the subject that we are discussing here, as I intend to convince you in the next slides. Please, the next slide. I would like to start thanking Professor Cláudia Saia and Pedro Araújo for inviting me to be here today and to deliver this talk to you, and also to thank colleagues, students, partners, and funding agencies that made this presentation possible, and also that built some of the figures that I will present to you in the next minutes. Next slide, please. Yeah, the outline of my presentation will include some general information about our group so that you can understand why we are working in this field. I will present the definition of the problem as the way we see in our group, so that our remarks and the way we see the challenges and perspectives for the near future can make sense for you. Then I will present some general results, again, present some general remarks, and finally some final conclusions. The next slide, please. So I will start with the group presentation. Please, next slide. We are a group of approximately 50 researchers working in the general field of polymerization reactions. We are 4 professors, and there are about 40 to 50 graduate students working around. So it's a very large group working in this field. Please, next slide. We do things like that you are seeing now in this slide. We basically produce polymer materials and polymer grades for different applications. We have been developing polymer materials, particularly for pharmaceutical and biomedical applications, because this is a very interesting field of investigations with many opportunities, but we are also working with commodities. And as we do lots of experiments producing polymer materials, we are also very interested in understanding the kinetics of the polymerization and building simulation environments so that we can manipulate the polymerization processes appropriately. Next slide, please. And we have a small pilot plant that allows the production of about 200 kilos of polymer materials per batch. This is very important for us because it allows the scaling up of the technological solutions that we develop in our group. This pilot plant is supported by some very important institutions that work in the biomedical field in Brazil, such as Fiocruz, which has been fundamental in the COVID-19 crisis in Brazil at this particular moment. Please, next slide. And as you all know, the plastic wastes constitute a major problem for those who are working in the field, and we cannot neglect the accumulation of plastics in the environment and in landfills. For this reason, we have been working quite a lot in the particular field of chemical recycling in order to transform plastic wastes into valuable chemicals that can be used in the chemical chain, and we can certainly include LPG among these many valuable products that can be obtained from plastic wastes. Please, next slide. We count on a small pilot plant, actually with capacity of 10 liters, that we use to produce larger samples for characterization performed most of the times by partners who work with us in some research projects. And we are now working on a plant that will have the capacity of 100 kilograms per hour in order to process the plastic wastes that are generated by the Federal University of Rio de Janeiro daily in the university campus. Please, next step. I would like to present some general definitions so that we can have a common vision of the problem. Please, next slide. First of all, we must definitely say that the problem of plastics recycling and use of plastic wastes must be 100% aligned with the principles of circular economy. So basically, we would like to keep the carbon atom circulating in the chemical and economical chain and see the wastes as a usable feedstock for manufacture of other chemicals. So this is very important, and I believe that when we talk about manufacture of LPG from wastes, we must definitely take into consideration the fact that the process must follow the principles of circular economy. Please, next slide. When we talk about recycling of plastics in particular, there are many opportunities for reuse and recycling of these wastes. We all know very well, and the field of mechanical recycling is very well developed, but we see many opportunities in the regarding chemical recycling, which is the main topic discussed here by the experts who are present in this meeting. And it's important to say that only approximately 1/3 of the wastes can be recycled mechanically. So we must develop feasible chemical routes that may allow the recycling of wastes through chemical process. And we can certainly also talk about energy recycling and in a certain sense, the manufacture of LPG regards this particular recycling route, which is connected to the use of the energy that is stored in the carbon bonds. One point in this figure is that it emphasizes the fact that there are many possible alternatives for use of the plastic wastes, and therefore all these alternatives must be considered simultaneously and compared to each other when a particular solution is developed, and we must keep that idea in our mind. Please, next slide. A very interesting point regarding plastics is that many plastics can be used to capture and store carbon dioxide in the solid phase. And this is very interesting because in the case of plastics, we definitely have the opportunity to close the carbon dioxide cycle. And this must also be taken into consideration by those who are interested in manufacture of fuels in general and LPG in particular. Another point that we can see in this figure is that the recycling of plastic wastes also give us opportunities to manufacture hundreds of different chemical compounds. And therefore, when we are talking about LPG or any other product, we must necessarily take into consideration these many alternatives and competitive products in order to be able to design feasible processes, both in terms of the economical aspects and also in terms of the environmental impacts that this process may cause in the environment. Please, next slide. And I would like to emphasize that we engineers, I'm a chemical engineer, we engineers are very good in making mass balances, energy balances, momentum balances, but we are generally not so good when we are talking about environmental impacts. We must also consider necessarily that the processes must be simultaneously economically and environmentally competitive. The fact that you are recycling a material does not mean necessarily that it's good for the environment. That is a confusion that is made by many naive engineers who think that only because they are using wastes, the process is appropriate or adequate. We must necessarily make all the environmental balances before deciding for a particular chemical route or production of a particular chemical compound. Please, next slide. Whenever possible, we should use feedstocks as available naturally. In our case, we should be able to use the plastic waste that are contaminated. We already know that cleaning, separation, purification many times leads to a very bad process from the point of view of the environmental impact. So feedstocks should be used preferentially as available in nature. In the case of wastes, as usually available in most landfills. Please, next slide. So I would like to present some general results and additional remarks. Next slide, please. One point is that when we are talking about using plastic wastes for manufacture of chemicals in general and LPG in particular, and if we are using the wastes as available in landfills, these wastes are certainly contaminated with biomass. So if we intend to understand the process and the products that we will obtain, we must also understand how pyrolysis of biomass will perform in a real chemical process. This figure is intended to show that the fractions, in the case of the gas fraction, where we generally find propane, butane, and LPG, and also the liquid fractions where we generally find the heavier oils, we see many times the smallest fractions present and obtained after the pyrolytic reaction. The pyrolysis of biomass leads to huge amounts of aqueous phase, or materials, compounds that are soluble in water because of the amount of oxygen available contained by the biomass, and also leads to huge amounts of solid materials that contain minerals in general that are present in most biomasses. But one interesting point here is that these fractions depend on the used operation conditions, which means that somehow we would be able to manipulate the amount of gas or liquids or solid that we obtain through proper manipulation of temperatures, heating rates, residence time, and so on, which give us a signal that this process should necessarily be optimized always as functions of the available feedstock. Please, next slide. It's not only the fractions that are subject to significant variability, but also the compositions of each particular fraction. So we see here that also the amounts of carbon dioxide, hydrogen, and methane are subject to significant variations as functions of the operation conditions. And one important point here is that biomass leads to significant amounts of carbon dioxide in the final gas. This carbon dioxide should be removed from the gas or might be used as a feedstock, as discussed in the previous presentation by Bogdan. As a matter of fact, the manufacture of syngas from available carbon dioxide streams concentrates most of the patents that are produced in the field of carbon capture for manufacture of chemicals nowadays. So this can be seen as a problem, but also as an opportunity. Another point that we must see in this slide is that we do not see propane or butane in any significant amount present in the gas stream. This should be taken into consideration. Please, next step, or next slide. We see similar variability in the liquid fraction. One problem is that the liquid fraction contains oxygenated compounds that leads to significant reduction of the burning power of the oil, and this should be considered, especially one important field of investigation regards the development of catalysts that can remove these oxygen atoms from these chemical compounds while still keeping these chemical components in the liquid phase. Please, next slide.
Professor, sorry to interrupt you, but we need just to finish, maybe to try to go for the discussion.
Okay.
Right?
Okay, so please, we see some variability in the liquid phase, the same variability. Please, next slide. And when we talk about the plastics without the biomass, again, the scenario is very similar and very important. It's very sensitive to the addition of different catalysts that we can use to modify the pyrolyzed stream. So the catalyst exerts a fundamental role in this particular process. Next step, please. Next slide, please. And again, once more, we see the variability of chemical compositions and chemical yields, and again, as functions of the catalyst. Please, next slide. And when we talk about biodegradation and the use of microorganisms to produce these streams, there is a lot to do in this field because most times the gas compositions are poor. They contain lots of methane and carbon dioxide, and it's very difficult to obtain other compounds of higher molar masses in the product stream. Please, next slide. And I do not believe that you will read this slide, but it's only intended to show that we need a particular microorganism for each particular plastic that is present in the waste. This constitutes a major technological challenge in the moment, because we need to engineer microorganisms that can transform mixtures of plastics and not only a single plastic material. Please, next slide. And all this variability leads necessarily to opportunities for design of different flow sheets and optimization. It's important to say that nowadays there is no single flow sheet that can be used for manufacture of products in general obtained from the pyrolysis of plastic wastes. Please, next slide. So my final remarks, I just would like to highlight that plastic wastes can indeed be used for manufacture of LPG through biodegradation and pyrolysis, although there are many challenges regarding the separation, removal of carbon dioxide, removal of oxygenated products, development of suitable catalysts and microorganisms which can be seen as biocatalysts, and also for the design of flow sheets and optimization of these flow sheets, as the yields and compositions are very sensitive to modifications of the operation conditions. So thank you very much for your attention.
Thank you, Professor José. So following our discussion session, probably I just asked you to have 10 minutes for the discussion section, session before the break. So I'd like to invite Dr. Valverde Pontes, professor from University of Bahia, and the speakers to answer some questions. And in the same way, for the last session, if you don't have time for all the questions, perhaps we can continue in the chat. Okay?
Thank you. Thank you very much for the nice talks and the complementary discussions. So I have seen already in the chat that Dr. Kalsi has already answered some questions about the supercritical gasification and another possibility feedstocks. And if I can make a different question that has already been answered in the chat, then actually two questions in one because of the time. So I wanted to know about the share of DME at the Q process, because you mentioned that you has a multi-product process. So you produce jet fuel, hydrogen, and DME. So how's the share of DME? And also, I would like to know about the logistic cost, because we have in the previous block, we have a discussion about the logistics of waste biomass, and you mentioned that you use both, every kind of waste residue. So how do you deal with the centralized production and the transportation costs?
Sure, and I think one of the key themes here was, and I'll address the feedstock first. One of the key themes here was that the production is actually not centralized; it is decentralized. So typically, and the graph that I was showing, and I'm sure the presentation we shared later on showed you the typical catchment area of waste that is available in typical European context, but it's very similar in the US and very similar in many other places, where you will typically only find 200,000 to 300,000 tons. Yes, you can go to some very larger cities and find 1 million tons together, but those are far and few between. So normally you are not going to very easily find more than 200,000 to 300,000 tons of waste very easily without having to transport over long distances. Okay, so that means that the project that you do is fundamentally limited by that scale. You're limited to doing it at 200,000 to 300,000 tons worth of input scale. And so you're going to have multiple projects which are producing this DME, because feedstock with its very low density will travel a lot worse than DME, which can be liquefied, and the amount of gigajoules per lorry, if you like, are a lot higher if you do it on DME. So the solution is an inherently decentralized solution. It's not like a refinery where there's one large plant in the middle of the country and everything comes to it. That's just not viable. The carbon footprint alone would be very significant from doing that. On the second aspect, which is what we produce, so yes, we produce a gas that contains hydrogen and CO, and we can produce hydrogen from it by removing, let's say, water gas shift, and then removing the CO, or converting the CO to hydrogen and CO2, and then removing the CO2 to make hydrogen, or we can put it through a Fischer-Tropsch process to make diesel and jet fuel, and from that comes out some propane butane. Our process for DME, and this is why it is effective at smaller scale, is it produces only DME. So our bulk production is DME focused, it's not a little byproduct. It is the primary production focus, and that's what makes it cost effective, in that it's not just a small offshoot, if you like. There's a very, very small amount of methanol which is produced as a byproduct from that plant, but it's 1 or 2%. You know, so everything else is just DME. So I don't know if that answers your question.
Yes. Okay, thanks. And then I'll make a question to Dr. Bogdan. So you presented some interesting options for pathways for producing syngas, like the co-electrolysis and the solid-driven dry reform. And then we know that when you consider the CO2 hydrogenation from the power-to-X concept, the most significant cost is the water electrolysis to provide hydrogen. So how do you rate the energy consumption of the co-electrolysis in comparison to the water electrolysis?
So the electrolysis of the water compared to the electrolysis of
both co-electrolysis. Carbon dioxide and water.
Well, I assume in this case, it will depend on the ratios that you have. So the amount of CO2 that is going to be used, and then the amount of hydrogen that is needed for the additional. So to add it to, because depending on the product, you will need to have different ratios of CO and hydrogen in Syngas. Depending on the feedstock that you have from the thermochemical processing, you will have a specific ratio of CO, CO2, and hydrogen in your product gas. So depending on these things, you will need to adjust the amount of water that you hydrolyze to achieve your final syngas that you will use further for your process.
Okay, thanks. So I see here that Professor Zakas is answering in the chat the other question. Then, since we are running out of time, so we have just 1 minute, I leave to you other question, also from the chat. So what are the suggestions that you can leave for the students that are following the theme and interested in synthesis? So what's the message you can leave for the audience?
Well, in my opinion, this is a subject of the 21st century. So if I were a student at this particular moment, I would certainly be involved with the topics that we are discussing in this meeting. And particularly, I would certainly encourage them to study environmental impact balancing, because we are not very good at doing this yet, unfortunately, and we have to improve a lot to understand what process actually will be beneficial for the environment and when compared to another one.
So thanks, Priscilla. So thank you very much for the very nice presentations. Yeah.
Okay, so thank you for the speakers and for the participants for the questions. So now we have a 10 minutes break before we start the session 3. So that means 11 a.m. for Brazil time and 3 p.m. for UK. So we can keep connected here and come back for the session 3 in 10 minutes. See you soon.